Hello, and welcome to our series exploring the Automated Drone Image Analysis Tool, or ADIAT. My name is Charlie Grove. I'm the Director of Technology for Texas Search and Rescue and the creator of ADIAT. Before we move on, I want to take a moment to say thank you very much for being here and for your interest in ADIAT. Whether you've been using the tool for a while now or this is your first time seeing it, we hope these videos are helpful as you go on your journey. Through them, we'll be doing a deep dive into the ADIAT interface, kind of showing you that end-to-end experience of how we use it to analyze images today. And then we'll be talking about the specific algorithms we have in place, both the RGB image algorithms and the thermal image algorithms that were introduced in version 1.3. Finally, we'll talk a little bit about a couple of advanced features we have in place to help augment the algorithms that we have. Before we do that, though, this first video, we're going to focus on a little bit of background information and some information about the tool itself and the underlying technology and computer vision that is used to make all this happen. Best place to start, though, is let's talk about why do we have a tool like ADIAT. And the reason we do is, in our use case for search and rescue, one of the more common ways to use a drone is to send it up in either through autonomous flight software or manually have it fly essentially a pre-prescribed pattern, going back and forth, taking pictures at regular intervals so that we can essentially create a quilt of images saying that, this entire area has been covered and it's been covered from multiple angles so that we know, hey, we have full coverage here. The drone then comes back and we take those images and then they need to be analyzed. And that's where we create this bottleneck because the drone will come back with 2, 3, 400 images after a 20-minute flight. And traditionally, somebody will have to manually go through each one of those images, looking pixel by pixel to say, is there anything of interest in here? As it's doing that, the drone is up flying again, comes back, more images, more in the backlog, and it just, again, it's that bottleneck that needs to be cleared so that we can go through and say all these images have been searched and there are areas of interest or there are not. What we do with ADIAT is automate a lot of that. We're going to take that same set of images when they come back and very quickly run it through our algorithms, looking for either a specific color range or anomalies, or if they're thermal images, looking for a thermal range or anomalies and saying, hey, the computer found something of interest in these 5 images. Let's either take another look at them or send the drone back up to go back to the area and see if there's anything there, or send a ground team out to see what is in that area. So given that background, let's go ahead and dive into a quick presentation talking about ADIAT, computer vision, and a few UAS best practices. All right, as we said, we're starting off with a little bit of background information about ADIAT itself, talking through a little bit of the history and a little bit of a technical overview for the application. First, though, starting with an even higher level overview of the application itself. I do promise for the majority of these videos, I'm not just going to be reading walls of text at you from slides. Just so happens that's where we're starting off because we wanted to provide a high-level overview, just a one-slider of, hey, here's what ADIAT is and how it came to be and how we're using it. To that end, the Automated Drone Image Analysis Tool, or ADIAT, is a platform and set of algorithms that can be used to programmatically identify areas of interest in a set of digital images. And the analogy I like to use for this platform versus algorithms is kind of like thinking about an electric drill versus the drill bits. The drill itself never really changes, that is the platform in this case, and the drill bits or algorithms are interchangeable depending on your use case and what you are trying to accomplish. For our purposes, if we're talking about, looking for a specific color in an RGB image, we'll be using either the color range or matched filter algorithms. If we're just looking for anomalies, we might use a different algorithm. And certainly if we're looking at thermal images, we will be using a different set of algorithms there. The primary use case for this tool is to aid in the analysis of photos taken by UAVs during search and rescue operations. However, there is nothing about this that is specifically limited to search and rescue or even UAV images. These tools, these algorithms will work for just about any image set that is out there where you are looking for either anomalies or colors or anything of that nature. This tool was developed as an open source project for the SAR community. We'll talk a little bit more about what that means in a minute, but if you are interested in helping in the development of the project, please feel free to reach out to us at info@texar.org, and we'll make sure to put that email address in the description of the video as well. All right, moving on to the history of ADIAT. So this is something we've actually been working on for quite a while now, so I'm not sure when these videos will find you, but it's currently July 2024. And we have been working on this for a good 7 years at this point, starting all the way back in 2017. At that point, Texar, our search and rescue team, did not have its own drone team, but we had an industry expert come in and explain to us how he was utilizing drones for his operations, and talking a little bit about some of the pain points of the analysis process and the very manually intensive process of going through image by image, pixel by pixel, and looking for the subject or whatever happened to be in those images. So as the IT guy, I started to think, I bet there's a technology solution that would help make this process a little more streamlined, or at least give us a first pass at doing some of this analysis. So very much command line based, hacked together, by no means productionalized code at that point. 2018, we went ahead and put a user interface on it to make it a little more user friendly, and still completely internally facing. We weren't really sure it was going to go anywhere, but just wanted to make it a little more user friendly in case somebody other than myself was going to end up using it in the field. 2019, it continued to grow, and we thought, this is actually a really reasonable product at this point. We're happy with where it is, and we actually released version 1.1 to the public and made the code base available on GitHub as a open source project. Honestly, didn't really think much about it after that for a little while. I don't think the industry was quite there yet, and drones just weren't accessible yet or accepted yet as part of search and rescue and similar activities. So we released it, but really nothing became of it until 2023. So this thing had been just kind of sitting there on our website. We hadn't really talked about it much. We certainly hadn't publicized it or pushed it, and people kept reaching out to us. They would find us through email and say, hey, we found your tool called ADIAT. Can you tell us a little bit more about it? Is it still something you're actively working on? What's going on with ADIAT? So I said, I guess we've gotten to that point where there's enough teams out there using UAVs. I bet it's time for us to pull it down and give it a full refresh and really start to bring it back together, because there's obviously a need for something like this. So in late 2023, we released version 1.2 with significant performance improvements over what we had in 1.1, as well as the addition of a third RGB algorithm that would be the match filter algorithm, and a couple of advanced features that we'll talk about in a later video. Now, version 1.3 has just been released with support for Mac OS, as well as thermal image algorithms and video parsing. So exciting new features, expanding the breadth of what you're able to support from a platform standpoint, from an image standpoint, and from a file type standpoint. All right, looking at the technical details of what is behind the curtain with ADIAT. ADIAT was built in Python, which is a computer language, and it utilizes a number of open source libraries. So there's an incredible amount of computer vision related stuff out there for Python that has been made freely available to the public. That was actually one of the big drivers for us deciding to make ADIAT open source as well. I was, all this stuff is out there and has made ADIAT possible. It felt right to go ahead and make ADIAT a part of that open source community as well. It has been compiled into Windows and now Mac OS applications with installers for portability and ease of use. There is one caveat here, and we'll talk a lot more about this when we get to the actual thermal algorithm video, but thermal image analysis is not available on Mac, and that is due to the limitations in the software provided by the actual drone manufacturers, unfortunately. So the good news, bad news, version 1.3, we do have an RGB, or we do have a version of ADIAT available on Mac OS, but it only supports the RGB algorithms at this time. Third item on this list, given that search teams often operate in austere conditions, ADIAT was built to run as a standalone desktop application without the benefit or a dependency on internet connectivity. So we often find ourselves in areas where we either have questionable internet coverage or no internet coverage, and the last thing you want to do is be uploading gigabytes of images so that they can be processed offsite. The whole backbone of ADIAT was, or one of the core tenets of ADIAT was, we're going to do this in a way that it can all be done on the computer in front of you, the laptop in front of you, the desktop in front of you, whatever it is. As long as it has the ability to run Windows applications or Mac OS applications now, you can go ahead and run ADIAT. It was designed to allow for scaling based on the capabilities of the user's computer, so you can scale up and down based on the hardware that you have available to you. Obviously, the better the hardware, the faster it's going to run, but there is no minimum computing power necessary for ADIAT. So even if you only have a laptop that's a few years old available to you, you should still be able to run ADIAT. It just might take a little longer to get through some of the image analysis. The modular structure of the codebase was also designed to allow additional algorithms to be added with minimal changes to the core functionalities. So back to that platform versus algorithm discussion, or switching out drill bits in the drill, if you will, the algorithms work the same way. So if we decide to add additional algorithms later, like we did with the thermal algorithms, or if somebody else or we decide to add new algorithms for RGB, very easy to do so, does not require significant changes to the core code base. Finally, as mentioned, this is an open source program. The source code is freely available in GitHub, which is a popular repository for open source projects, along with instructions on how to run and compile the application. So if you're not familiar with the concept of open source, it is pretty much literally what the words say. It is the source code is openly available to anyone that wants to go ahead and download it, and they can go ahead and make improvements on it and adapt it for their needs, and hopefully contribute to the overall program so that we can continue to move it forward. As far as licensing goes, ADIAT is licensed under the GNU General Public License version 3.0, which makes it freely available to use for anyone in the community. There are some limitations, and you can see those here. Namely, this is provided free to the community. There is no expressed warranty with it or guarantee of support. That being said, we are always here to help support, and as the community grows, there will be additional people in place to help support if issues come up. If you have questions on how to use the tool, by all means, there will be avenues available to provide support to you. Jumping over now, we're going to go ahead and talk about computer vision, which is the technological backbone of what we're doing with ADIAT. And if you're asking, what the heck is computer vision anyway? Here's a very high-level definition. So computer vision is a field of computer science that focuses on enabling computers to interpret and understand visual information from the world, such as images and videos. It involves developing algorithms and models that can process, analyze, and make sense of visual data in a way that is similar to human vision. So that last statement is really powerful. Essentially, what we're trying to do with computer vision is make a computer work sort of the way, or as close as possible, the way sighted humans' eyes and brains work together. We interpret the visual information that comes from our eyes and our brains, without us even noticing, interpret what we're seeing. We can identify colors, we can identify shapes, we can identify objects, all those sorts of things that are, second nature to us at this point have to be taught to a computer, and that is the field of computer vision. Now, what does that actually look like? So if we see an image like this of the Afghan girl, I think most individuals will see this, and the first thing they see is the subject herself. Then they see her piercing eyes, they see her red garments, they see the green and the green background. A computer pretty much does the opposite. It doesn't see the whole image. It sees the individual squares of color called pixels that make up the image. So it isn't seeing the girl. It isn't even seeing the eye. It is seeing a block of color. In this case, this kind of gray color. In fact, because computers are digital, they can only understand at their very core ones and zeros. So at the end of the day, everything has to be a number for a computer to understand it. So it doesn't even see the color gray. It sees a numeric representation of the color gray. If it wants to see the entire image put together, it just sees this giant table of sets of 3 values where each set of 3 values represents 1 pixel. And what we're trying to do with computer vision, what we're trying to do with ADIAT is work with a computer that can only see this giant table of numbers and get it to see things the way we see them as humans. For a real world example of that, we have our Texas Search and Rescue field uniform shirt. And I think most folks will agree, if they saw this shirt and somebody asked them, hey, what color is that? The color that would come to mind is probably something along this shade of orange. Now, what happens if we take that same shirt and we take it out of the studio in the perfect conditions with tens of thousands of dollars of photography equipment and put it out in the real world? Suddenly, that orange shirt looks like these orange shirts. And it's no longer just this color because, again, the computer is seeing each individual pixel. So it's going to see this shirt and it's going to see this color over here. And it's going to see this yellow color up here. And it's going to see this orange color down here. And it's going to see this orange color down here. And that's where we need algorithms for tools like ADIAT. So we can say, hey, ADIAT, I want to go look for this orange color, but no, it might actually be some combination of these colors. And all of those need to be interpreted as being that same color of orange, or at least close enough to that color of orange that we can say, hey, this matches what the person was looking for. Let's go ahead and flag it as an area of interest. One other note as we talk about computer vision, so artificial intelligence is huge right now in many facets of our lives. It does absolutely have implications in computer vision as well, but it is not an area we're delving into quite yet in ADIAT. I do expect us to in the very near future, and we're very excited about that. So what is the difference between traditional computer vision and artificial intelligence as applied to computer vision? Well, with traditional computer vision, it's going to see this image and say, hey, I see something red, or I see something that is a close approximation to the red value that you provided me. Once we move over to artificial intelligence, specifically something in the image classification space, it'll take a look at this and say, okay, I recognize that circle is a tire, that circle is a tire, those look like headlights, windows, etc. Puts all those pieces together and does what you and I have been doing since we're 2-3 years old and says, hey, that's a car. So impressive, the leaps and bounds that we are making in artificial intelligence, and we absolutely hope to utilize it in the near future in ADIAT. Now, so far, everything we've looked at in computer vision is specific to RGB images, which only utilize information from the visible light spectrum, which is this little sliver right here out of this whole spectrum. There's all sorts of other stuff out there in gamma rays, X-rays, UV, infrared, and radio waves. And the good news is there are drones out there that are able to leverage portions of the spectrum beyond visible light. We see stuff with LiDAR that utilizes lasers in the infrared space for mapping activities. We have multispectral drones that can show us stuff in the red edge and near infrared, so right up here just past the visible light spectrum. Those are really useful for a lot of vegetation analysis processes and other things of that nature. And perhaps most importantly to us right now, we also have thermal drones, which are also part of the infrared spectrum. Now, if you're curious how a thermal camera works, a thermal camera works by detecting infrared radiation, which is emitted by all objects based on their temperature. The focused infrared radiation is captured by a detector array, which converts the infrared radiation into an electronic signal, and the electronic signals are processed and converted into an image. Now, you may be thinking, okay, this is computer vision. We just saw the definition of computer vision. Computer vision is about getting computers to interpret visual data the same way humans do. Well, now we're talking about stuff that's beyond the visible light spectrum. So is it technically computer vision? Maybe not by the strictest definition, but there are a lot of parallels in the data and a lot of parallels in how it's structured. So for our purposes, the analysis is pretty darn similar. Oddly enough, when you get down to it, the image analysis for an RGB image is actually a little more complicated than a thermal image. For an RGB image, for each spot in the matrix, the table of pixels that create the image, you have 3 values to contend with the red, green, and blue channels. Whereas for the thermal data, once you take the underlying radiometric data and convert it to actual temperatures, you just have a single value representing each pixel. So it's kind of the equivalent of analyzing a grayscale image versus a full color image. So getting to that with getting the radiometric data and converting it into actual temperatures can be a little more cumbersome and a little more complicated. But once that process is done, the actual analysis is even a little more straightforward than RGB images. As I said, because we just have a temperature, there's not a full colorization available to us. It is literally just a temperature, and any visualization we have of that data is literally just for show and to make analysis easier for humans. There is nothing about the actual underlying data that says that this temperature array should look like this image here versus this image where we're going with, hotter objects are black versus the original one where they were white, or applying artificial colorizations where we now have yellows and reds and all those sorts of colors, or another colorization where we have purples and oranges and yellows and all these colors. All these visualizations are just to help with analysis. There is nothing about the underlying data that specifically lends itself to one coloration or another. And we'll dive a lot deeper into that as we look at the thermal image algorithms. But for now, we are going to move on from computer vision and talk a little bit about UAS best practices for image analysis. This is the last section we'll be covering in our first video here. And as I said, we'll be talking a little bit about some of the best practices that can be implemented for the UAS pilots so that they can provide the raw data to us for image analysis that'll be most effective in ADIAT. And what that looks like, if we have a list here, is, hey, fly consistent height, consistent speed, consistent direction, consistent distance between image captures. The fewer variables we have in collecting the data, the better off we will be when it comes time to do the analysis. There are a number of mechanisms that will allow us to do this, but I would highly recommend, if possible, to leverage some sort of autonomous flight control system. There's a number of third-party applications out there, and a lot of probably the higher-end drones have their own software that allow you to pre-program what is usually called a mapping mission. If you want to get that set up and just say, hey, fly over this area, give us 100% coverage with whatever overlap and whatnot, go ahead and do so that we can use those images for our analysis. And that brings us to our second point, which is that fly overlapping passes to maximize coverage. So seeing things from slightly different angles, just a few feet over, can make a dramatic difference when you're looking at shadows or tree cover or those sorts of things. So just because an area is covered in one image doesn't mean we won't get additional information by covering it a second time. We're talking less than a second per image to do the analysis here. So the more images, the better. If possible, keep the camera gimbal set at -90 degrees. So this gets kind of technical for the non-UAS folks, but basically what we're saying is keep the camera pointed straight down if possible. The images that come back with the UAV are geo-tagged, so it has the GPS location, but it's the GPS location of the drone itself when the image was taken. If it's gimbaled at a high angle, like, it's 45 degrees, and you may be looking at something that's hundreds of feet, if not further away from the actual drone and GPS location that is stored in with the image. And when and where possible, try to limit changes in lighting conditions. So sometimes it's not possible, but again, it's all about controlling the variables here. If you can have the same sort of lighting conditions throughout the entire data set, then the same color orange is going to look the same in all those images. One of our advanced features helps try to combat this a little bit, and we'll talk about that in a future video. Second area I want to talk about for UAS best practices is ground sampling distance. So if you do a lot of mapping missions, you're probably familiar with this concept. Ground sampling distance, or GSD, refers to the distance between the centers of two adjacent pixels on the ground, measured in units such as meters or centimeters. In simple terms, it represents the ground area covered by a single pixel in an image. So when you zoom all the way into the individual pixels on an image, how much actual on-ground real estate is represented by that single pixel? Now, if you're curious as to how ground sampling distance is calculated, here's the formulas for it, both GSD from a height and width perspective. It's calculated based on the flight height, the actual physical sensor size, the camera sensor size. Now, I know a lot of them have a nominal size saying, oh, it's a 1-inch CMOS sensor or something like that. Now, we need literally the physical dimensions of the sensor when it says sensor height and sensor width in these two equations here. And then the denominator is the focal length multiplied by the image height or image width, depending on which formula you're looking at. For an example of what this looks like, so I put my target out here. This is my little landing pad. It is 19.5 by 19.5 inches. I went up to an altitude of 100 feet, and the target size at that altitude with my DJI Air 2S was 2,971 pixels. When I go up to 200 feet, it goes down to 743 pixels. When I go up to 300 feet, we're down to 330 pixels. When we go up to 400 feet, we're down to 185 pixels. Why does this matter? Obviously, the higher you are, the smaller objects on the ground are going to appear, which means there are fewer pixels for us to pick up on saying, hey, that's our area of interest. So the lower we can fly, usually we're better off because it increases the size of what we're looking at on the ground. The other concept we'll look at is overlap calculations. So as I mentioned, there's a lot of benefit from doing overlapping passes as well as overlapping image spacing going in a straight line. So as part of flying a search pattern, the pilot must establish the distance between images and passes that will allow for a consistent margin of overlap. So how do we calculate overlap? First, you have to understand the footprint of an image, and we can see those calculations here. We're essentially saying, okay, we know the GSD calculation, multiply that by the image height, the number of pixels in the image height, or image width for the footprint horizontally. And that gives a sense of what the footprint is of an actual image that is taken from the drone. Then determine the desired overlap percentage, front overlap as well as horizontal or side overlap. And we could do those calculations to see, okay, here's the distance horizontally, here's the distance vertically based on the footprint and the desired overlap. Now, what does this look like in a real life scenario? So we have my same setup here with my landing spot right here, dead center in the image. When I move over 50 feet horizontally, we have an 80% overlap. So for a 50-foot offset, we lose 20% of the information from the previous image, if that makes sense. If we move over 75 feet, we lose another 10%. Move over to 100 feet, we lose another 10%. We're down to a 60% overlap. And finally, if we're at 125-foot horizontal offset, we are down to a 50% overlap. So 50% of what was seen in the previous image is no longer visible to us. All right, that covers all of the background information I wanted to cover in this first presentation. I hope this is helpful to you. And starting the next video, we will dive into the tool itself. Thank you very much.